So here we're going to talk about the different interpretations of the derivative. So application problems, the words rate of change often means that you will take a derivative. So you see rate of change in there, you should be thinking, all right, I'm going to take a derivative at some point. Be careful. The derivative finds the instantaneous rate of change, okay, which is, this is another definition of a limit, all right? So you've seen the definition where it's a limit as h goes to 0 of f of x plus h minus f of x over h. This form right here would be if you had h equal to x minus a. Okay, so that would be the substitution you would make to get to this down here. All right, so if you think about it, this is finding the slope of secant lines. So you have 2 points, 1 point A, 1 point X, f of A and f of X, and you're finding the slope of that secant line in there. Okay? So that's the instantaneous rate of change. But there's also the difference quotient, which finds the average rate of change, which is simply this piece without the limit. Okay, y2 minus y1 over x2 minus x1. Right, so two different things there, so you got to be careful. Are they asking you for the average rate of change, or are they asking you for the instantaneous rate of change? Instantaneous rate of change is the derivative, and the average rate of change is the difference quotient, the slope. So in general, if f is a function of x, then the derivative of f prime of x, measures the instantaneous rate of change of f with respect to x, okay? Now, typically in applications, you're talking about physics applications, x is usually an independent variable time, okay? So the derivative answers the question, when x changes, at what rate does f change? So this is the question that the derivative answers, all right? When x changes, at what rate is f changing? Okay, so you think about it, as your x values change, how are your y values changing? The study of motion, okay? So I'm gonna let s of t measure the distance traveled, how far we've traveled, in feet, of an object after t seconds of travel. Then the derivative, s of t, has units as feet per second. Feet per second. Why? Because it's saying how many feet has changed over some given amount of time, right? When x changes, how does f change? So feet per second, you're taking your feet, you're dividing by your seconds, okay? So s of t is measures the instantaneous rate of distance change. It also measures the velocity. The velocity v of t, okay? So for your textbook, to find the velocity function, what we do is we take the derivative of the position function, s of t. And so when I take the derivative with respect to time, with respect to t seconds, then that gets me the velocity function, okay? And my units for the velocity function is feet divided by seconds. When you think about, you think about speed, the velocity, absolute value of velocity is your speed. We'll talk about that more later, but when you think about like 55 miles per hour, that is a velocity rate, okay? It's a rate. It's units or the distance divided by the time unit, okay? Now, let's think for a second. Let's go a step further. Just like we took the derivative of the position and get the velocity, what happens if we take the derivative of the velocity function? So the derivative with respect to time t, this is equal to a of t. Now, a of t is, in units, is feet per second, right? So you think about v of t is feet per second, right? But if I take the derivative again, what happens? I take feet per second, and that's where that second squared comes into play there, okay? So that's why the units for acceleration are the change in velocity, so the change in the change of position. Okay, so that's my acceleration. So the definition, it's the instantaneous rate of velocity change. The instantaneous rate of velocity change. All right, average acceleration. So this would be like if I had the sentence, you know, a car goes 0 to 60, it changes speed like from 0 miles per hour to 60 miles per hour in 3.7 seconds. Not bad, right? So that would be the average acceleration. It's the change in your velocity is the acceleration. So how fast is your speed increasing, or how fast is your speed decreasing, depending on whether you're slamming on the brakes or slamming on the gas, okay? So gravity, units of acceleration for gravity, in feet, we're going to use 32 feet per second squared. For meters, it's 9.8 meters per second squared. So those are the two numbers that you're going to use. So make sure you have these numbers down so if you're ever doing a physics problem with gravity, you know which one to use is based off of whether it has feet in the problem or meters in the problem. Okay? So there's a second interpretation of the derivative, the slope of the tangent line. So the second interpretation is the slope of the tangent line, okay? So here, the graphs of f and g are given, and I want to identify which function is the derivative of the other one, okay? So remember, the derivative is the slope of the tangent line, okay? So when I look at this, all right, it looks like f has negative slopes. So I've got negative looking slopes until I get to right here, and then my slopes turn to 0, okay? What that tells me is if I have negative slopes there, that means that the derivative f prime is negative, okay? The derivative is negative there. Well, guess what? Oh. Okay, so g of x is actually negative. G of x is actually negative on that interval there, right? But then what happens? Over here on this side, it looks like my slopes are positive, okay? So now I look at my positive slopes, that tells me that f prime is greater than 0. Well, guess what? At this part right here, f prime is positive, okay? Even though it looks like it's heading back to 0 here. But as you can see right here, my g function is actually equal to 0, but this here, that has a slope 0. So it looks like g of x is my derivative function. So this is the derivative of f of x. Okay, how do I write that out? If I take the derivative of f of x, it equals g of x. Okay, so whenever I look at that, I think about the slopes. Okay, so let's just for a second pretend like we didn't know, like we were still stuck on this problem trying to solve it, and we thought the other way around. Okay, so we'll see why the other way would not have worked, right? So say we thought g was the function and then this was g prime, right? So what do we know? Well, the slopes here are positive, okay, until we get to right here, and then the slopes are 0, and then over here the slopes are negative. So if I was going to graph this, I would see, all right, right there I've got a 0 slope, so that actually lines up okay. But then this tells me that the derivative is positive, so that means that the graph actually needs to be above the axis over here, okay? So it would actually be above the axis over there. But then over here, the derivative will be negative, and so that means this is negative over here, okay? So you see, this graph doesn't match what it should be with the red graph. So you can see there that it kind of falls apart on you, okay? So you look and you know, first thing you might do is just figure out, all right, I know I've got a 0 here. Well, guess what? That lined up. I know I have a 0 here. That lined up. So that didn't eliminate anything for me. But after I get my zeros, then I can say, okay, everything on this side should be in the negative side. Is the other graph below the x-axis? Sure, g of x is below the x-axis here. So that worked out, okay? And it didn't work for this one because here I've got a positive slope, but then over here this is negative. Even though it is positive eventually, it doesn't really work out for you, okay? So the good thing about this, we're negative coming here, and we're negative there, and then we go to being positive here, and then we're positive on the output of my slopes here. All right, guys, hopefully this gives you a little bit better understanding of what the actual derivative is, okay? So the second interpretation is the slope of that tangent line, okay? So at this point right here, I have a slope, okay? I have a slope, right? And if I'm trying to plot this, if I plot this right here, maybe this is an output of m equal to 1.5 or something, and then therefore I get this plotted out at the 1.5 level. If I plot my slope here, I get an m equal to 0, and that gives me a 0 here. If I plot it here, it looks like it's starting to level off again, so maybe that's an m equal to 0.2, right? And so that's where I get my 0.2 going on right there. Okay, so you can see from this graph, you can actually tell that this point is the highest g value, which is equal to f prime, right? So that means that this point on the graph is actually the most steepest of the positive slopes, okay? All right.